So unfortunately, I didn't really give you any room to put some notes, so maybe you want to put them off to the side here. I'm going to do it on a separate page here. We looked at this once before already in our overview, but I just want to reiterate it. So let's say we have this function here, f of x, and then let's say we have this function right here, g of x. And let's say I'm trying to find the area between these two curves, between x equals a and x equals b, meaning I am looking for this quantity right here. Oh, that looks kind of like a double helix. Anyway, let's say I'm looking for that quantity right there. Well, it turns out that this definite integral that we've built is built in such a way that it handles this just fine. So I want to reiterate how we could think about this. Okay? One way we could think about this is let's find the area underneath the upper curve. Okay? So what is the area between f of x and the x-axis? That would be the integral from a to b of f of x dx. That would give me what? That would give me this amount right here. Right? So I could find the area underneath the blue curve, right? Using my definite integral as a tool. Okay. Then what could I do? I could find the area underneath the red curve. And what would be the area underneath the red curve? It'd be the integral from a to b of g of x dx, right? That's the area underneath the red curve. So what is the green, the quantity that I'm trying to find? The area between these two curves. It's simply blue minus red, right? It's simply the area underneath the blue curve minus the area underneath the red curve. Okay? Now, there's another way we could look at this, though, and that's to write it as a single integral of a to b of f of x minus g of x dx. So here I've put the two integrals underneath the same integral symbol, and I can do that because they've got the same limits of integration. Okay. All right. This is probably, even though this might be the way you might first develop it as this two separate integrals, this is the way I would prefer you to work with it because there's a handy way of saying this. What did we really do? We took the integral from a to b of the upper minus the lower. And this is the formulation that I think is the best. There are many other ways to piecemeal these together, right? There's many other ways to come up with that green area, but this is the way I think that is the best. It is the upper curve minus the lower curve. My math lab, when you do section 6.2, is going to kind of send you off on some fun tangents, thinking about how to do these different ways. Keep in mind that the definite integral computes the area underneath the curve and the x-axis, or the area between the curve and the x-axis. So there are many ways to piecemeal these together. I would like it, though, and I think you will have an easier time going forward, if you just keep remembering that we're taking the upper curve minus the lower curve. Okay. Now, and maybe if you got just a little bit more room somewhere else, we'll see. I'd like to do one more. So let's say this is our scenario here. Let's say I'm looking for the area between these two curves. What's different about this problem from the last one? Yeah, partway through it switches which function's above and which one's on below, right? So what do we need to do? We need to determine that point of intersection. Okay? So we need to figure out where this is, and to do that we probably need to actually know what the function is, but let's call that point C. And so then how would we find the area? We would say that the area is simply the integral from a to c of f of x minus g of x dx plus the integral from c to b of g of x minus f of x dx. Now, there are many other ways. In fact, I heard somebody say minus. I could have put a minus here, but then I would have had to have kept these in their original order. So there are many other ways to do this, but I'm sticking with that initial formulation that I gave you of upper curve minus lower curve. And that will always give you the total area for that region, and then so then you're just adding those two positive numbers together. Again, my math lab, when you practice this, will have you slice and dice things into all sorts of interesting pieces. Great, it's good practice, it's good exercise. Okay? But eventually you want to return to the idea of just simply doing upper curve minus lower curve.
So do you plug both A and Z into both functions?
Correct. So you would find, so if you wanted to evaluate this, you would take capital F of x minus g of x, evaluated from A to C for the first part, plus capital G of x, and here I'm using capital to stand for an antiderivative, minus capital F of x, and yeah, so there is some C to B. There is some extra work here. For instance, you're computing G of C and F of C twice. Okay? But notice that and those two middle quantities will they cancel each other? Yeah, they'll cancel each other out. But anyway, I'll let you explore how that works. Okay? But the thing that I want to make sure everyone understands is you can just stick with this formulation. So we were really careful in the way we defined the definite integral, and it's pretty robust, and it allows us to do these sorts of things. So you can just give yourself kind of these simple mnemonics of upper minus lower. Okay? This works. You don't need to put this part down. This works even if we're below the x-axis. If here's the curve f of x, and here's the curve g of x, and I'm looking for the area between these two curves, I'm still going to do upper minus lower. It still works out. Okay? Now, why is that? Well, this will give me a negative number, right? But then I'm going to subtract from it this larger negative number. And what's one negative number minus a larger negative number? It is the positive area, and it is the correct area. So you don't have to worry about where these are in the quadrants. Now again, my math lab's going to have you do some piecemeal. They're going to say break this up in some unusual ways. That's great. It's good exercise. You should learn how to do that. Okay? But you just stick with upper, and by upper I mean in the y sense, which curve is above the other curve. Okay? I've got a question. What if you don't know which curve's above the other curve? You plug in two test points. Plug a test point into both of them and see which one's above. Solve for when they're equal. Like let's say these two curves intersected at 2 points, right? So you would solve for when they're equal. Say this happened at right here at L, and this happened right here at M. Then you would put L and M on a number line, and you'd take a test point in between L and M and plug it in and just see which one has the larger value. That will be your curve on top. Okay? So you don't actually have to see the graph to answer these questions, although oftentimes we pick simple ones so you can graph them so life's a little easier. Okay? All right, let's do some problems. We'll do this first one all together. Here I gave you a picture. That was nice of me. Actually, I just copied it. I think it's from your book. Okay. I didn't have to give you a picture, though, and in later ones I will just give you the functions and expect you to draw the pictures. Okay. But here I gave you the picture. Okay. So let's see here. It seems to me that the black curve is above the red curve, right? So we're going to do the integral of the black curve, which is x, minus the red curve, which is x squared minus 2. Okay? Be careful, folks. When you subtract a function, you better put it in parentheses. Everyone catch that? Who didn't follow what I just said? I need this parentheses right here, or else I won't remember to distribute this negative at some point, right? That's why I need to make sure I put that second function especially in parentheses. Does that make sense? Okay. What remains to be done? Yeah, we don't know what the limits of integration are. Okay? Sometimes I'll give them to you. Sometimes you'll have a nice graph and you can read them off the graph. But oftentimes, what will you have to do? You'll have to solve for them. How am I going to do that? You're going to set the two curves equal to each other. So let's go ahead and, even though I didn't label them this way, let's call one y1 and the other one y2, just so I can refer to them by name. So let's set y1 equal to y2. So that would happen when x is equal to x squared minus 2. What do we do? Well, let's solve this equation. This is algebra. So we get 0 is equal to x squared minus x minus 2. You could use the quadratic formula if you want. But this factors to be x minus 2, x plus 1. So this happens when x is equal to 2 or when x is equal to minus 1. Boy, I sure gave you enough room. That's unusual. So now I think we're ready to put up our limits of integration in this integral. We're going from -1 to 2. And let me just re-emphasize. I want to bring this back home again. Let me re-emphasize these are from the x-coordinates -1 to the x-coordinate -2. Or excuse me, to the x-coordinate 2. Okay. So let's go ahead and answer this one. So I'd like you all to do this. Go ahead and solve. Folks, I got 9 halves. Do I have a confirmation on that?
Yes.
All right. Folks, I do want to, I mentioned this once before and I want to say it again. If this problem were worth 6 points, if you get to here, you've gotten 5 out of 6 points. At least 5 out of 6 points for getting to here. Okay? So please separate the calculus, which is everything up until we get to this line right here, with number crunching, which is this line right here. Okay? So as you're doing your homework, sort of allocate your time in such a way that you're saying, hey, this is extremely tedious. I think I got the idea down. I'm going to move on and try some new problems. And quite frankly, if I were taking a test, I would do the exact same thing. I would get to here, and then I would move on to another question. Get through all the questions, and then come back and worry about computing this. Okay? Does that make sense? Because this is just a computation here, and at most it's worth 1 point. Okay? So please try to separate the calculus aspects from the number crunching aspects, because it is hard to come up with these problems and have them have nice limits of integration and nice intersection points and an interesting picture, and also work out to an easy number to compute. That's pretty rare, okay? And it's more important that we have nice intersection points than it is the actual answer comes out nice. So oftentimes these will be messy fractions. This one's actually not so bad. All right. So let's have you try the next one. I don't think these are numbered. Let's have you try the next one. Time, I want to just keep going. Sorry, we're just going to do it, and then we'll work some different ones. So let's see here. We need to first, well, we can start setting up the integral. That the area is going to be the integral of what? Black minus red. Everyone okay with that? Upper minus lower, right? Okay. Now, again, my math lab will have you do some crazy stuff in finding this area, and then finding this area, and then subtracting the two. Just go with the flow. You're just piecemealing things together. But I'm going to stick with my formulation of upper minus lower. Okay? Now, what else do we need to be able to evaluate this? Limits of integration. So when does the cosine curve and the minus sine curve, when do they agree with each other at the same angle? Probably where? At your pi's over 4 multiples. Let's figure them out. Let's see here. I would think this one is probably 3 pi over 4. Let's just check that. What's the sine of 3 pi over 4? Oops, maybe not. What's the sine of 3 pi over 4? It's the square root of 2 over 2. What is minus the cosine of 3 pi over 4? Yep, okay, good. Where that works. And then I think this should be minus pi over 4. Okay. So we get x equals minus pi over 4 to x equals 3 pi over 4. Okay. Folks, I'm not going to evaluate this one. But I'm not saying this one's easy to do. Be oh so careful with your negative signs with this one. This one is a real doozy with negative signs. If you get an answer of 0, have you made a mistake? Well, for this one, I think we can say, usually you'd say not necessarily. We're looking for this physical area. So yeah, if you get an answer of 0, if you get a negative number, you've made a mistake on this. Okay. Does that make sense? All right. All right. This one is another one. You try. This used to be a final exam question for my students, but nobody ever got it right, so I stopped asking. All right. Now, this is something that we start introducing in this section, and that is being able to integrate with respect to y instead of with respect to x. Before I talk about that, because I don't think I've talked about that in this class. So I'll talk about it in just a moment, it just takes a second. But let's go ahead and we'll do this problem the hard way first, which is integrating with respect to x, which is what we've been doing. Okay? Let's look at this problem for just a second and let's see what the issue is. We said that when we do this, we're slicing like this, right? And what was my rule of thumb? We take the what curve minus the what curve? The upper curve minus the lower curve. But look what happens, and it's this is blurry as it is. Ooh, I'm never going to fix that. This is blurry as it is, but let me try to zoom in on it anyway. Okay. So look at this. Okay, who's the upper curve as I've been drawing it? This red curve. Who's the lower curve? This black curve. Okay. Oh, what just happened? The red is both the upper and the lower curve. Okay. Right? So I can always tell when I look at this problem, I can always tell who's going to get it right and who's going to get it wrong pretty doggone early, because the people that got it right drew some of these little rectangle marks and realized it, and the other people just jumped right into the problem. So draw these dx thin slices going the way the rectangles went in our Riemann sum when we integrated with respect to x. Okay, so what I'm drawing here is what? I'm drawing a bunch of arbitrarily thin rectangles, right? And this is the way they ran, and we're doing upper minus lower. Okay? So let's see here. In this case, this function was solved in terms of x instead of y. Okay? So we better switch that around. So this is equivalent to this. Right? These are the same lines. The line x equals 2y is equivalent to the line y equals 1/2 x, right? How did I get there? I just solved for y. Okay? Likewise, this is the curve x equals y squared minus 3. It's equivalent to, when I solve for y, let's see here. I'll have y equals, and I'll have an x plus 3, but then I'll have to take a square root, right? By applying the square root method. And when I do so, what will I have? A plus or minus. So that's actually going to give me two separate functions. So I'll label the first one y1 is the positive, and y2 is the negative. How we doing, folks? And let me go ahead and underline this one in green. What is that represented by? That's represented by this positive square root function. And let me represent this one in blue. Which one is that? That's this negative square root function. So I think we're almost ready. We just need to go ahead and find some points of intersection here. Okay. Well, let's see here. This is the ordered pair. It's on this curve right here, right? And it's where the y-coordinate is 0. So this is the ordered pair minus 3, comma 0. And let's see here. This is where these two curves agree with each other. Well, where does that happen? Well, that either happens where blue, let's see here, let me give this guy a color. Where blue and yellow, if I think of this one as yellow, even though I know it's already black, but it's either where blue and yellow intersect, which I don't want to solve those two, right? Or I could say it's where these two curves, I'm running out of options. It's where these two curves intersect. Let's just figure out where those two curves intersect. So this happens when 2y is equal to y squared minus 3, or when 0 equals y squared minus 2y minus 3, or when 0 is equal to y minus 3 times y plus 1. So this happens when y equals negative 1, or when y equals positive 3. So which one is this one right here? This is the one where the y value is negative 1. If y is negative 1, then x is negative 2. How did I get that negative 2? I plugged it back into anything, well, anything that it goes through. So I could have plugged it back into blue here, or I could plug it up into this one, but it made most sense to plug it into this expression right here. I put a negative 1 in for y, and I got that x is negative 2. Okay, so where's this point over here? So the y-coordinate is 3, and then Sarah says plug 3 into that circled equation right here, and you get that x is 6. Great. So there's a little bit of work you have to do. So we're ready now. Let me. Well, that's not going to work when I zoom out. So we're ready now to give the area in terms of x. In terms of integrating with respect to x, as I drew these dx slices, right? So the area will be the integral from x equals minus 3, right? That's when I started. That's where I first started drawing these rectangles. And I'm going to break this up at x equals what? Negative 2. Why did I stop at negative 2? Because that's the transition point where I switch between which curve's above and which, well, the curve on top stays the same, but the curve on the bottom changes. So it's going to be green, which is the square root of x plus 3, minus blue, which is minus the square root of x plus 3. Do those cancel? Heck no. If you ever get 0 for one of these actual areas of a region, then you've made a mistake. Now, if you're doing a net, right, if you're doing a definite integral, where you're not, that can happen. Okay? All right, so that's this first part, and let me just emphasize. Pink, okay. So here we go. Oh, that doesn't really work, but okay. That's this guy right here. That's what we just found. Right? So now what do we need to do? We need to add to that what's left. So we're going to add to that the integral from negative 3 to 6.
Shouldn't it be from negative 2?
Oh, negative 2 to 6. Thank you. From negative 2 to 6. Okay, so what am I trying to find here? Let's do, I don't know, making this thing all sorts of ugly. Oh. We're doing this part right here. Yeah.
It's like modern art.
Okay. Who's the upper curve now?
Green.
Okay. It's still the same one, right? It's still the square root of x plus 3, but now who's the lower curve? Yeah, who knows what color it is anymore. 1/2 x. Okay. I am not going to evaluate this one. And in fact, the direction, well, maybe, no, the direction, yeah. Set up, but do not solve. This is very typical for me to give as directions for these problems. I'm concerned with, can you set up the problem? In other problems, you'll have shown your ability to evaluate definite intervals, right? So let's just worry about setting this up.
Isn't it easier to just like do it with respect to what?
Yes. We're going to repeat this problem here in just a second.
On a test, will we be like forced to do it this way?
Well, let's look at the directions on this one. This one said, set up but do not solve with respect to x and one with respect to y. Okay. Which is, if you look at your practice, your 2 practice finals, I did ask 2 questions. Each final exam, I've asked a question where I've had you do both directions. Okay, any questions on that? This was hard for 2, 3, 4, I don't know, a few reasons. Okay. Put aside the messy colors. This was hard. The main reason why this was hard was because halfway through, when we integrated with respect to x, which curve was on the bottom changed. So we had to break it up there. The other reason why this was hard was because I originally gave you the functions in terms of y, and x was a function of y, and we had to switch it around so that y was a function of x. Then we had to find limits of integration, so that involved finding intersection points. Okay? All right. Any questions on that? Because I got to erase this and then move it. Actually, I'm just going to erase it. All right.
Are you recording this?
Yes. Yeah, weird things are happening.
Sometimes you just gotta freak out while you're releasing. It's just good.
All right. So, the entire Riemann sum process can be redone from scratch, where we draw the rectangles. Let me put it up on the board like this, where we draw the rectangles going this way. As long as we have as long as we have the equation x is a function of y, then all we do is we input a y value and it tells us how far to the right the rectangle is. So I'm not going to redevelop the entire Riemann sum, but we could give a new limit definition, and we would say then the area of this would be the integral from y equals c to y equals d of f of y d what? dy. Okay. Where what in this case? This would be y equals c, and this would be y equals d. Okay. So be careful here, folks. And this is an important skill for Calc 2 especially. My rectangles now go left to right instead of bottom to top. They now go left to right. That's how my rectangles go. But I stack them one on top of the other instead of one to the right of the other. So my limits of integration go bottom to top. My rectangles go left to right. My limits of integration go bottom to top, as opposed to how we initially did it, right? Initially we did it this way, and initially we had our rectangles were going bottom to top, right, up to down, right? And we were stacking them left to right. Here I'm stacking rectangles on top of one another. Okay? So when I represent this idea of integrating with respect to y, the way I represent it to myself is by slicing having the rectangle sliced this way. And think about that word slicing. It's a good way of thinking about this. Okay? In our partition, 5.1 word, in our partition before, we sliced with respect to x. Now we're slicing with respect to y. Okay? So, other than that, everything is exactly the same. So here, when we integrate with respect to y, we're going to do the rightmost minus the leftmost. From y equals c to y equals d. So why is that beneficial in this problem? Say that again. Go ahead.
So it's equivalent to doing upper minus lower?
Yes.
It's just on a different axis.
Exactly. So instead of doing upper minus lower, we're doing right minus left. So it's the same idea. Why is that beneficial for this particular graph? Notice in this problem, the function that's always to the left is the what function? The red one. And which one's always to the right? The black one. Do we have to worry about breaking it up halfway through? No. So we still need to find this point of intersection. Well, I'm not going to redo it. This is still the ordered pair, minus 2 minus 1. What's that? Okay. And this one is still 6, 3?
Yeah.
Great. Okay. So now I'm going to do this, we're going to integrate. So who's my rightmost curve? So now I'm going to give, now it's x is a function of y, so I give the expression in terms of y. So this was, the rightmost was black, which was 2y, minus the leftmost, which is red, which is y squared minus 3. We're going to integrate with respect to y, and it's going to go from y equals, what is my, remember, how do I stack these rectangles? One on top of the other, so I start off with the bottom rectangle. Where was my bottom rectangle? When y was -1, up until y equals 3. Do you see why we've started labeling those limits of integration? It just helps you keep your thoughts straight. Do I require it? No, but I still think you should do it until you hear the cat's meow. Now this one, I don't think would be hard. I think it would be perfectly fair game to say go ahead and evaluate this one. Well, maybe not, because you still get fractions. But it's certainly a lot easier to do the antiderivative step, whereas the initial one, besides being, oops, I've erased it. Besides being broken up into pieces, it had a bunch of square roots, and taking antiderivatives of square roots often involve u substitutions, and those would have. Where are we? Is that a whole page? How you feel? Great. Yeah. Okay, so there's more of these. So let's do this one real quick. We'll do this one with respect to y. So the area would be the integral from y equals 0 to y equals 4 of the square root of y minus y over 4. Double check me. We didn't say upper minus lower, we said right minus left. What curve is to the right here? Well, actually, before I even do that, before I even answer that question, I'm integrating with respect to, let's draw some y slices so we're sure of what we're doing. Here are some y slices. Do you see them? Okay, so now it makes sense when I say what's the right end of all those rectangles? It's the red curve. What's the left end of all those rectangles? It's the black curve. And so then we did right minus left. And what was our, well, this is the ordered pair 0, 0, right? This is the ordered pair, just for fun, this would be the ordered pair 2, 4, whereas this would be the ordered pair, I don't know, 1, 4. If you want, that's the ordered pair 0, 4. Doesn't matter. Where do we stop drawing our rectangles? When y gets up to a y value of 4. Could you integrate this with respect to x? and I don't think it'd be terribly hard. You could integrate this with respect to x, but look at the rectangles. For a while you would do black minus red. So we would say the area is the integral from x equals 0 to x equals 1. And what's the black curve? It is 4x minus red. What's the red curve? It is x squared. Folks, what did I just do there? In my head, I solved them for y, respectively.
Did you do it like geometrically too?
Yep. Yes, so that's what my math will have you do, right? It'll have you compute, you know, various subregions and you piecemeal it together. Yeah. Okay, that's just an exercise in logic, has nothing to do with calculus. Right? That's just an exercise in logic. So if I want to talk about this region right here, I could find this region, or I could find this amount and then subtract from it this amount, and that would give, there's lots of ways you can combine numbers. Okay? All right, but that's just until we switch which curve's above, right? And so then we would have the integral from 1 to 2. Now, who's the lower curve? The lower curve is still x squared, so I'll still be subtracting x squared, but the upper curve is now 4. Oops, that's not an equal sign, that's a plus. So this would give me the area if I integrated with respect to x. It's not the end of the world, but certainly integrating with respect to y was easier. Well, maybe. It's got a square root in it. So, I mean, there's just different ways of looking at it. Okay? But you want to get comfortable integrating both ways. Now in Calc 2, sometimes you'll only have the option of being able to integrate one way. So you kind of look at a problem, you say, well, let me try it this way. No, that's going to be too messy. Let me try the other way. Do we want to do anything else? No, that's good.